Are we on the verge of the next energy revolution?
A hugely expensive alternative energy project is going full speed ahead.
It's one of the most ambitious science experiments in history.
But whether it's a sure shot or dead end depends on who's telling you about it.
Scientists in California recently announced a major breakthrough in nuclear fusion power.
I mean, this is something generations of physicists have tried and failed to do.
Breakthroughs in fusion have been announced before, so is this just another empty promise?
Fusion power almost seems too good to be true. 1 kilogram of fusion fuel has the same potential power as 10 million kilograms of coal. And that same kilogram of fusion fuel could power 10,000 homes for a full year, all without the same pollution or greenhouse gases that come from fossil fuel.
Entire cities could be powered with zero carbon emissions.
Imagine no diesel motors, no gasoline engines. Like imagine rush hour traffic without exhaust fumes.
Safer, cleaner, and more efficient than fossil fuels and the nuclear reactors that we use today.
Clean, limitless power.
Fusion has this almost limitless potential because it's essentially like bottling up a star.
If you look out a window into the sky,
Okay.
that big, bright, glowing thing,
Okay.
that is a fusion reactor.
Fusion is literally what powers the sun. But there's still a huge question.
Can we bring fusion power to light up our electricity grids, much like it lights up the sky from the sun?
Scientists have been trying to harness the power of fusion for generations.
Our hope is to make laser fusion reactors in the early 80s and perhaps have a prototype reactor going in the 1990s.
Fusion energy has been a dream since Albert Einstein was alive.
The joke that critics often make is that, fusion is something that's always going to be a mirage in the distance, that it's 10 years away and always will be.
But scientists haven't given up. They're still trying.
Scientists have been looking at the basics of fusion since the 1920s. Can you think of any other scientific endeavor that we've pursued for 100 years nonstop?
I still get chills, actually, when I think about what this means for our field and what it means for all of the people that have devoted their lives to this.
It's a great way to get yourself out of bed to be working on such an exciting problem.
After decades of attempts and failures, scientists may just be close to making fusion a reality.
We're within striking distance of actually being able to generate more energy with fusion than we put in, which is a critical step towards making this viable for making electricity.
It will be hard, and there's still a lot of things we need to figure out, but I do believe we can make it happen.
The implications of all of this research are pretty extraordinary. It's just a matter of when.
I'm Noam Hassenfeld, and this week on Unexplainable, fusion power could completely transform our world and fix our energy problems, all while putting us on a path to a climate change solution. But is it actually possible? And how long should we keep trying? Okay, Umair Irfan, senior science reporter at Vox.
Hello, Noam.
I know fusion power has all this world-changing potential, but what is it exactly? How does it work?
Fusion is sort of taking tiny atoms like hydrogen, the smallest chemical element, literally number 1 on the periodic table.
Top left,
and you're smashing those tiny atoms together so hard that they stick. And then it forms a new atom, helium.
And why does combining two atoms create so much energy?
Well, you've heard of Einstein's famous formula, E equals mc squared, right?
Of course, my favorite formula.
So this is where it actually comes into effect. Because when you're taking these hydrogen atoms and you're smashing them together, the new atom that results, helium, actually has slightly less mass than you would expect. The whole is actually less than the sum of its parts by a tiny amount. And that's because matter is being converted into pure energy. In that E equals mc squared equation, remember, m is mass, the c is the speed of light, and the speed of light is already a big number. So when you take the speed of light and square it, there's this huge multiplier effect you get when you convert mass directly into energy.
Yeah, like every bit of mass you lose is multiplied by the speed of light squared. So that much energy. Every little bit of mass times a ridiculously huge number.
Exactly.
We are playing with Einstein's equation.
I talked to a physicist named Tammy Ma. She's a researcher at the National Ignition Facility, also known as NIF.
And what we would like to do is, in the laboratory, harness that reaction and control it in a way that could give us a clean energy source.
How clean of an energy source are we talking here?
Super clean, probably one of the cleanest energy sources we've ever come up with. We're talking about no carbon dioxide, no particulates, no nitrogen oxides, no sulfur oxides. And there aren't, tons of this radioactive nuclear waste you get with conventional nuclear reactors. So on almost every front, this is cleaner and better than anything else we've tried.
Our project with the National Ignition Facility, if we can make it work, it is a solution for all of humankind. It's clean, it's environmentally sustainable, and it can help meet the needs of the entire globe.
And what is NIF like, this laboratory where Tammy is trying to harness fusion power?
It's huge. It's one of the most powerful scientific instruments ever developed.
It's in a building the size of 3 football fields, side by side, 10 stories tall.
I went there, I think this was 2012, 2013. It was before I was a U.S. citizen, and so I had to actually go through a big background check in order to be there, because it's a big part of that lab's mission is nuclear weapons simulation. So they have a really powerful supercomputer, and when NIF isn't working on fusion, it does nuclear weapons work. You're not allowed to be anywhere by yourself. You have somebody with you at all times. And you go inside and it's these towering pieces of hardware. It's really hard to even make sense of what you're looking at. You see all these big tubes that are winding through the facility. And you then walk towards this core where they're actually doing the fusion. And you see it's sort of this spherical device. It's hard to describe, but literally it looks like, something that would be on a spaceship.
The NIF facility was used as the set of Star Trek Into Darkness. So our target chamber served as the warp core for the Starship Enterprise.
But it's also a research lab, and it's surrounded by bubbly scientists who like talking about their work.
I get to play with these huge, really fun toys.
This laboratory uses the world's most powerful laser system to try to trigger a fusion reaction.
It's actually 192 separate lasers, each one alone one of the most energetic in the world.
How do these lasers exactly accomplish fusion? What are they actually trying to make here?
So they start with this tiny fuel pellet. It's about the size of a peppercorn, and they zap it with these extremely powerful lasers.
And what you're trying to do is take a fuel capsule that started about 2 millimeters in diameter and squeeze it down to about half the diameter of a human hair, keeping it round the entire time.
Think about compressing a water balloon. If you're squeezing a water balloon in your hands, but you don't want it to extrude through your fingers, so you have to confine it evenly along all sides and compress it at the same time.
As you squeeze, everywhere it can, the balloon is going to squeeze back out.
It wants to squirt out towards any kind of gap it can find.
And so you can imagine how difficult it is to do this compression symmetrically.
You want to try to confine it in as small a space as possible, but all the forces in nature are working against that.
Okay.
In the nucleus of an atom, the protons, they're positively charged. And, you may recall from playing with magnets, like poles repel. And so it's kind of like that here at the subatomic level. You have to overcome these intrinsic forces. These are also very tiny particles. Imagine trying to aim 2 billiard balls at each other, but they're sub-microscopic, right? You're playing a very, very delicate game of pool here. So you need to have enough kinetic energy. You need to have the atoms moving so fast past each other that if they end up aimed at each other, they'll overcome that resistance, and then they'll collide and they'll stick. And that's the challenge. You're working against some of these really powerful forces at the atomic and subatomic level.
The way she's using this laser, is this sort of an exciting new development? What's the significance of this?
Oh, this is a massive project.
The laser energy, it starts out at a fraction of the amount of energy that you might have inside a laser pointer, and we amplify that up 1 million billion times.
This laser beam is traveling almost a mile around this facility as it bounces between mirrors and amplifiers and gains more power.
Until you have the most energetic laser in the world.
They charged up the laser.
Countdown started at T-minus 255 seconds.
Insert the target.
3, 2, 1, shot.
Bam, they fired the shot and they caused a blackout.
Ironically, even though we are generating a little star in the laboratory, all of the bulbs blew out. And so the facility actually went dark.
Okay, seems promising.
Blackouts don't happen every time they run one of these experiments, but it shows you just how much power is being used and just how much they are at the cutting edge of this, that, they're still testing the limits of their equipment. Even designing a machine to do this has been a scientific endeavor in and of itself. In order to start the fusion reaction, in order to ignite it, you need a really powerful spark. It's like, putting a match to a campfire. You put in an initial amount of energy, but once that energy is there, the reaction generates its own energy and propagates itself. And these lasers, these most powerful lasers in the world, are supposed to provide that spark. But of course, to power the most powerful lasers in the world, you have to use a lot of energy. And so we want more energy out than we put in. And that threshold is called ignition.
So they're shooting super lasers at hydrogen atoms, and they're hoping that if they put enough energy into them, they can force them to fuse and hopefully ignite a process where more and more atoms will continue to fuse.
Right. And recently they reported that they came closer than they ever have. And they say that now they're basically a hop, skip, and a jump away from being able to get more energy out than they put in. Like, they think that this is now achievable. Like, they have a pathway towards energy positive fusion based on the most recent results they got.
Wow, that's super exciting.
It definitely is. And I think the scientists there are pretty jazzed about it.
Oh my God. Yeah, I was jumping up and down. I think many of us were.
The fact that they're able to get the fuel burning at this level and get this much energy out of it means that the changes that they need to close the gap are not qualitative. They're incremental. That basically they think with a lot more fine tuning, they can close that gap and eventually get there. So this does not seem like an impossible task anymore. This does not seem like it's something that's entirely theoretical. This looks doable. Like they're climbing the mountain and they can actually see the peak now.
After the break, what would we need to make the dream of sustainable fusion power a reality? And is it worth the risk? That's next.
The power of the sun in the palm of my hand.
It's Unexplainable. We're back here with Umair.
Hey.
So scientists are closing in on break even, which is this point where they can get as much power out of a fusion reaction as they actually use to trigger it in the first place. So what's left here? What's standing in the way of getting to break even?
There are a lot of technical and scientific challenges here that they still have to overcome.
Okay.
It's kind of unique as a scientific challenge and as a scientific mystery because the goalposts are fairly clear. And we know it's doable in theory, but in practice, like, what is it that's holding us back? It's the engineering challenges, designing the machines, the devices. And as scientists have been pursuing this, they keep finding out more things that they didn't know. Mm-hmm. In fact, they developed this whole subfield of physics, plasma physics, to try to understand fusion because it involves a whole new state of matter.
I think I know what a plasma is. Sort of like this fourth state of matter, right? It's like not a solid, not a liquid, not a gas.
Exactly. You know, you have the conventional ones you've learned in school. You know, think about water. When it's frozen, it's ice. When it's liquid, it flows as water. And then when you heat it up, it turns into steam. But if you have it at much higher temperatures and pressures, you can actually get another state called plasma.
Okay.
You know, this is what's formed in lightning, plasma is also what basically is going on in the sun as well. And we want to be able to do that in a laboratory and then eventually in a power plant. The trouble is that, because it's such a novel state of matter and because it only exists in these extreme temperatures and pressure conditions, scientists are still learning a lot about it. It's almost like a fractal. The more they zoom in on this, scientists keep finding more things that they need to learn about. And that's part of why the timeline for fusion keeps getting longer, because the more they study it, the more they realize they don't know.
What if this never happens? I mean, it seems like there's a possibility that fusion actually never happens, right? Maybe they've gotten close to break even and they never get to break even. They never get more.
It's possible. And that is a possibility that we have to be ready to deal with.
So if there's no guarantee of making fusion work, if this might never actually happen, how do we give ourselves the best shot of figuring out all the science we still don't understand?
So it's a technology problem. We've been still developing the technology on trying to get this to work better, but it's a funding problem as well, that we've had a hard time getting a consistent level of support. We're talking about hundreds of billions of dollars sustained over decades. So there's different ways you can do this. You have the private sector and you have these billionaires, Gates, Bezos, they're investing in some of these startup companies.
Sure.
Then there's government support like NIF, which is, kind of analogous to like the Manhattan Project, where it's done at like government facilities. And then in contrast to that, you have something like ITER, ITER. This is the big fusion experiment that's being put together in the south of France. And this is like this big international collaboration, this kumbaya, let's all come together and work towards a common goal. It's more analogous to something like CERN. And the reason we're starting in like the $1 billion domain is with fusion, unlike other kinds of science experiments, you don't start small and go big. You have to kind of start big and go even bigger. You're limited by the scale of materials. You're working with some very extreme temperatures, and you're working with cutting edge science. And you need a lot of very smart people working with some of the most advanced stuff in the world. And you have to do this on a scale large enough that you can actually achieve these results. And so the barrier for entry is really high.
But it sounds like we are spending a lot of money on these huge futuristic facilities and projects like NIF. I mean, are we not spending enough?
A lot of fusion scientists would argue that we have never funded fusion to the extent that it deserves to be funded. The U.S. Department of Energy did a study back in the 70s looking at the different pathways towards achieving energy positive fusion. And they looked at a scenario for a rapid all-out approach, for a middle tier approach, and for a slow long-term approach. And then they also looked at this fusion never scenario, where we only have a trickle of funding going into fusion that is never enough to actually achieve anything. And to date, we've been funding well below that level.
We've been funding below the fusion never level.
Correct.
And so we really have been on this fusion never trajectory for quite a while at the same time making scientific progress.
I talked to Troy Carter, who's a physicist who studies fusion energy, but also thinks about these big picture questions.
The truth is we have not really had a new facility that has enabled us to really push that energy to another scale for a few decades here, really. So without the investment necessary to take the next step, we have been in this holding pattern where we're making good progress on the science and understanding things very well, but we can't take that step to really see if we can make an energy source out of it.
So like the fusion reaction itself, we've never really invested enough to trigger an ignition.
We just need to put enough dollars in to enable that ignition to happen. That's right.
But there seems to be more buzz now around fusion, though, right? Like, could that mean more funding?
Yeah. Right now, there's a lot of attention on fusion because there have been some major developments. And there's also this concern about climate change that, we are going to need more sources of clean energy in the future. But we're also sort of under the gun here because we also need to start making changes to our energy system now.
Yeah.
The United States, for instance, has committed to cutting its greenhouse gas levels drastically by 2030. We already have an interim target that's less than 10 years away, which means a lot of those changes have to start taking place right away. Things like electrifying vehicles, but also shutting down fossil fuel power plants. And the question then is, when you have a finite amount of money and a finite amount of time, what's the best way to spend your dollar?
I could understand people saying you've been at it for a long time, you haven't gotten there, why do we continue to invest? But it's one of those things where, again, the level of investment for this important problem needs to be much bigger. It's a drop in the bucket compared to the environmental costs, compared to what we spend on energy. And there is absolutely no reason that we should be trading off one energy investment versus another.
And is it possible to do both here, like work on climate change now and invest in fusion for the future?
I mean, like fusion itself, theoretically, it is possible. And there's no reason we can't do it other than our own limitations of imagination and will.
But like, do we have enough money?
Money is made up. Carbon dioxide is real. It is a physical substance and it is heating up the whole planet. Money is made up. And so this is a decision we have to make in terms of our values. You know, when it comes to waging war, there's always money.
Mm-hmm.
When it comes to like other kinds of things like bailing out big industries, we can always seem to find the money. But when we look at something that is going to bear fruit decades down the line, when most politicians who are in office now will be gone, it's much harder to make that case. The person who signs the big funding bill for fusion energy and really gets this going probably won't be around to see the first fusion reactor power up. So who's going to take credit for that? And how do you explain to your constituents the money you're spending now for something that you won't see the benefits of?
Yeah, you know, something that I keep coming back to is like, this is a show, Unexplainable is a show about the unknown. And we're comfortable talking about things that, you know, might happen in the future. We don't fully understand now. We see the potential, this and that. When we're talking about hundreds of billions of dollars of tax money, when people are like, you know, when do I see the benefit of this? It seems like a hard sell to get people on board with something that may never even work.
That's true, but I would say it's not just about the destination, it's about the journey. You know, think about like the space program. You know, in practical terms, what did the US actually get out of going to the moon itself? It's not like we have a colony there. It's not like we're mining resources on the moon. But the simple process of actually pursuing something that's so far beyond anything we've attempted before unlocked a whole suite of new technologies, you know, from how you run an institution like NASA to the engineering of things like rockets to satellites. There's a lot of things that came out of the space program. Similarly, in our pursuit of fusion, we've learning a lot about things like plasma physics that we've been able to deploy in industries like semiconductor manufacturing. And as we build these materials designed to tolerate these super extreme conditions and come up with ways to contain them, you know, that has applications beyond fusion to other kinds of industries as well.
You know, I'm really taken by your comparison to the space program. And there's certain senses in which going to the moon in the 60s felt inevitable. Like the way that we tell the story now, it feels like, oh, we were always going to get to the moon. And I feel like a million things could have gone differently. And I guess if we're saying, you know, we need another investment on that scale, do you feel like something like that could happen in our future?
If you go back to the 1960s when they were funding the space program, I mean, you'll realize that, like, in terms of public polling, you know, people weren't all that in favor of it either at the time. A lot of people raised a lot of the same questions that we're talking about now. Is it really worthwhile to be sending people to the moon? Like, that sounds like a really frivolous thing to do, given, you know, the tensions of the Cold War, the economy, and a lot of the
civil rights movement.
The civil rights movement. You had so many other concerns on the table at the same time. And a lot of people raised those same questions at that time as well. Like, is this still a worthwhile endeavor? And so we could probably think about fusion as something like that, you know, we have a lot of sunk costs into fusion in terms of the research and development, but we're also making progress as well. And if we can carry forward this momentum and get more people interested in it and, you know, inspire the next generation of scientists who are going to be inheriting this project and actually carrying it over the finish line, you know, we potentially can achieve what may be humanity's crowning scientific achievement.
You know, Umair, if you were in charge of the budget, you know, if you are looking at, you know, hundreds of billions of dollars in front of you and you can take this money, do you feel like you would be confident enough in this to put that money in that spot to make this happen, to make that bet?
I was born into a world where the roads were already built, where we had international air transport, where we had dozens of vaccines that helped me survive childhood. And all of those investments were made by people I've never met, and many of whom never saw the results. And I think I owe it to the past and to the future to make the same kind of investment. And I would bet on fusion.
This episode was produced by Meredith Hodnott, that's me, with help from Noam Hassenfeld and Bird Pinkerton. We had edits from Catherine Wells, Brian Resnick, and Noam, who also scored the episode. Richard Sima did the fact check, Christian Ayala did the mixing and sound design, Mandy Nguyen is planning on getting a pet pigeon, and Liz Kelly Nelson is the VP of Vox Audio. If you want to get in touch, please email us at unexplainable@vox.com. And if you feel like leaving us a nice review or a rating wherever you listen to your podcast, we'd really appreciate it, and it would help other people find our show. Unexplainable is part of the Vox Media Podcast Network, and we will be back in your feed next Wednesday. Have a lovely week.